Welcome class, and once again we'll be kind of wrapping up some of our discussion, at least in videos, on thermodynamics and kinetics. And again, we're focusing on the kinetics portion of this. We've already discussed thermodynamics, and we said that, just as kind of a quick review, when you're dealing with both of these, thermodynamics is answering the question, can a reaction occur? And we said there's several math equations that we have to deal with. We have to consider two basic factors: the enthalpy of an equation or of a reaction and the entropy of a reaction. And then we can put those together in one equation called the Gibbs free energy equation. And depending on our answer there, we can answer our question, can a reaction occur or not? And then that led us to the realm of kinetics. And we said kinetics deals with two other questions. And the first one that we dealt with in our last video was, will a reaction occur? And what we saw was just because it can doesn't mean it necessarily will. There's some possible barriers that can stand in the way. And one of the key concepts there that we were introduced to was what we called the collision theory. And we said that there were kind of two key factors that had to be true in order for this collision theory to or for a reaction to happen. And we said that the collision theory said that your collisions between your reactant particles had to be forceful enough. We said part of that had to do with the issue of ultimately being able to break bonds. And the other issue was that they had to be properly aligned in order to form those new bonds eventually. So those two things have to be true in order for a reaction to happen. And if they're not, then that can possibly be a barrier to answering the question, will a reaction occur? We also said another barrier could be what we call activation energy. Activation energy being that minimum amount of energy I need in order for the reaction to begin. And we said that minimum amount of energy I need is to break the initial bonds of the reactants. I have to break the bonds of the reactants first before I can form new bonds. So I have to have an addition of energy first before I begin to lose energy in the reaction. And hopefully overall I have a greater loss of energy than I had to gain. But if that initial hump of energy that I have to gain is too large, it can stand in the way of the reaction happening. So those were a couple barriers, and we're going to kind of deal to some extent with those barriers today, or mention some of those. And that was more, will a reaction occur? We're going to deal kind of with the second question in kinetics, and that is, at what rate will a reaction occur? Or if you want to say, how fast will it occur? It's kind of the same thing. And there are several factors that affect that. So we are dealing with reaction rates is the kind of concept that we're dealing with here. And a reaction rate is how fast reactions change into products. And if you're looking at this visibly, sometimes it might take, it could be a long process, so it could take days or weeks or months in which for the reaction to occur. Other cases it occurs almost instantaneously. So there's a vast difference depending on what the reaction is. And so that's kind of what we're studying here, is what is that rate? And then here's the important part, and here's the practical part in chemistry, is there something I can do to manipulate this? Because we use chemistry all around us every day, whether it's in your house, whether it's in some factory that's producing something that you will use on a regular basis, whatever that might be. Obviously, if that's the case, I want to produce it as quickly as possible so I can get it out on the market. If something takes a week to react and I have to wait for it, that entire time, that's that much slower than I'm going to be able to get it out on the market. And so if there's anything I can do to manipulate it, and that's a lot of what we're going to be looking at today, is are there certain things that affect the rate? And a lot of these are things that we can manipulate and change to speed up. And what I'm going to want you to do ultimately is be able to explain, so not just list the factors that affect the reaction rates, but ultimately I'm going to want you to list those, and then also explain, well, okay, how does this particular factor, what's going on the molecular level? What's happening that would speed something up? And I would also expect you to tell me, is it going to speed it up? Is it going to slow it down? If I do this, it'll slow it down. If I do this, it'll speed it up. So all of those things I would expect in your answer as we go through. So the first one here, what are some factors that affect reaction rates? The first one is what we call concentration. And here's the key thing you may want to write next to this. What is concentration? Concentration, we're dealing with amount of something. When we say something's concentrated, if you think back to last chapter, we were comparing when we dealt with solutions. When we said something was a concentrated solution, it meant it had a lot of solute in the solvent. Okay, so when we're talking about concentration here, we're talking about amount that is in something. Okay, so if you have your reactants, and let's think of it this way. If you have a high concentration of reactants, then you're going to have a lot of collisions. And the more collisions you have, then, in essence, it's almost like probability here. Assuming that your collisions are forceful enough and properly aligned, or at least some of them are, the simple fact that you have more of them, more collisions, then you're going to end up with a faster rate. If I only have a few reactants in there, then those collisions are going to be few and far between. And since they're few and far between, and since not all of them are necessarily going to be properly aligned and forceful enough, then I end up with a slower reaction. So the greater the concentration I have, the more they're bumping into each other, and the more frequently they're bumping into each other, more than likely the faster it's going to go. And it varies from one reaction to the other. So there's no hard and fast rule, like if I double the concentration of reactants, then it will double the rate of a reaction. It depends, and it varies, and we'll take a look at that to some degree when we look at rate laws. So reaction to reaction can be different in how concentration affects it, but it does. The key thing to understand is this: the more I increase the concentration, the faster my reaction is going to go. If I decrease the concentration, then I can slow that reaction down. Now, if you think of the next one here, the next one is one you're familiar with, temperature. If I adjust temperature, now here's where you have to be careful. A lot of times we think of adding heat, and that's all we think of when temperature, but I can do the opposite as well. So understand, when I'm saying temperature, I can increase or decrease this, and depending what I do will depend on how it affects the reaction. Generally speaking, as I increase the temperature, the reaction rate is going to increase. And let's think about why. If I increase the temperature, what am I adding? I'm adding kinetic energy, okay? And so if I'm adding kinetic energy, those molecules are beginning to move faster. Well, let's go back to the collision theory. What was one of the factors that had to be true? They had to hit forceful enough, right? Okay, and force, that's an issue of energy. Okay, so if I'm increasing my energy, am I increasing the force at which they strike, okay, each other? Yes, I am. And I'm increasing the force at which they strike each other. And so I'm basically directly affecting one of the factors that is required for those reactions to occur, okay, in the collision theory. So as I increase my temperature, they're moving faster, they're striking each other with more force, and therefore your reaction is going to go faster. Generally speaking, about every 10 degrees Celsius you go up, your rate is going to double. Okay, now that's not necessarily a hard and fast rule, that's a general rule of thumb, kind of a guideline. And the opposite is true as well. If I decrease the temperature, I'm going to slow those molecules down, and so they're not striking with as much force, and so the rate begins to slow. A good example of this would be like milk. Okay, if you think of milk, We put it in the refrigerator, at least hopefully you do. Why? Because if you leave it out, it tends to go bad rather quickly. Milk has a natural chemical reaction where it begins to break down and produce, in essence, what we would call lactic acid. Um, and that the acid is what gives milk its bitter, sour taste eventually. So in order to slow that reaction down so it doesn't break down, so in other words, you drink the entire gallon of milk before that actually happens, we stick it in the fridge. What does that do? That's slowing that reaction down. It doesn't stop it, but it slows it down enough. Now, if you leave that gallon in there for weeks on end, eventually, even if you slow it down, it will happen. Okay, but that's an example of how we use temperature to affect a reaction rate right there at home. So you're using chemistry at home and you didn't even know it. All right, the next one again is surface area. We touched on this in the chapter on solutions, and we talked about surface area and the amount of like a solute that's exposed or something like that in terms of the amount of collisions there. Again, very similar, okay, kind of idea here. Is the more surface area you have exposed, the more collisions there can be. Generally speaking, smaller particles have more surface area exposed than do larger particles, because they need to break up before, and become smaller particles. So it's very similar to what we said before. We kind of compared the idea of a sugar cube dissolving and granulated sugar in there. The sugar cube is going to dissolve much slower because a lot less surface area is exposed to the water as that reaction between the sugar and the water and that dissolving process is going on. So the more collisions I can have, so this is again similar to concentration in the sense of the more collisions I can have, and the way I do that is to expose more of the particles or more surface area to those collisions. Makes my probability greater. All right, the last one is a little bit different, and this is catalysts. And sometimes students treat this as like a magic wand. You just stick in a catalyst and boom, there you go. Your thing automatically, your reaction automatically speeds up. And that may be what it appears like, but kind of have to understand what's going on with a catalyst. First of all, what is it? It's a substance that changes a reaction rate without being permanently changed or consumed by the reaction. So it doesn't directly, it helps the reaction, but it doesn't directly participate in the reaction in a sense. It is not a reactant, and it's not going to become a product. It's separate. In general, most catalysts speed up the reaction, and sometimes hundreds of times or thousands of times. You have a number of catalysts, often called enzymes, in your body, and if your body did not have them, you would die. Simple as that, because they speed up a lot of the reactions in your body. And basically, the kind of prevailing theory we'll call the lock and key theory, and basically what it says is that, or it's the idea that you have the catalyst particles. What they do is they kind of latch on and they help, in a sense, the alignment. Remember we said that you have to be properly aligned. In a sense, they help the alignment of the different particles that are going to attach together. Another key thing that a catalyst do is they lower the activation energy, kind of in the sense a lot of times they'll stretch the bonds to make it easier to break those bonds initially, so you have to put in less activation energy. So basically what they do is they're lowering the activation energy by sometimes stretching the bonds of a reactant, and then in theory they also kind of latch on to the particle and place it into whatever other element it's going to attach to form that new substance. So that's kind of how catalysts work and help speed up reaction rates, is by lowering that activation energy and helping the alignment. So those are the four factors that we're going to kind of take a look at that affect reaction rates and what I would expect in terms of you being able to explain them. We'll talk about a couple other things in class as well, but that's it for today.